Okay, so now let's quickly discuss what's the difference between order and molecularity. So if we take an example of a rate law which looks something like this, b raised to the power b and c raised to the power c. If this is the rate law that is given to you, okay, then the order of the reaction becomes the summation of these exponents, right? Whatever that is, okay? These can be positive or negative numbers. How can it be negative, right? It can be negative because there are certain things that if you increase the concentration of certain things in that reaction might actually inhibit or slow down the rate of the reaction, and those things will have the order as negative. So this is the overall order of the reaction, A plus B plus C, but individually the rate of the reaction will be order A with respect to this component, order B with respect to this, order C with respect to this, right? So there might be certain things which might have a positive order and might increase the rate of the reactions when their concentrations are increased, and vice versa when they're negative. They can also be fractional numbers. So there is no problem with your rate having fractional numbers, right? They can be fractional numbers, they can be positive or negative, and even they can be zero, right? They can be zero. They can be zero too. Like if you increase or decrease the concentration of that particular component, nothing is going to happen. So those kind of reactions are called zero order reactions. Like photochemical reactions are generally zero order reactions. Okay, so we are not going to deal in detail what are the different orders of reactions and what are the mathematics of this. This will be done in another full-fledged kinetics course. But in here, just remember that okay, the order, this is the overall order of that reaction, and individual components can also have individual orders. Okay, and they can be positive or negative numbers, they can be fractional numbers, they can be zero. Now there is a difference between the order and molecularity, right? So molecularity, it's basically a simple concept. So it's the number of molecules that have to come together to collide that gives you the molecularity. So there could be two molecules that are coming together. So it could be A plus B is giving you some products. So the molecularity will be 2. If it is 2A plus 3B, then the molecularity becomes 5, something like that. So it's just the number of molecules that are coming in and giving you, and that is taking the reaction forward, right? For an elementary reaction. Again, for an elementary reaction, this should be true, okay? Now this was calculated experimentally, right, from some elementary reaction. So molecularity can also be calculated for elementary reactions. And molecularity can only be positive numbers, right? And it could only be positive, like it could be natural numbers, right? It has to be positive and it has to be whole numbers, right? Or natural numbers. Why? Because you cannot have half molecules reacting. So you have to have some kinds of like whole number things going on in here for molecularity. You cannot have negative or zero or fraction. You cannot have fractional. So you get the point between what's the difference between order and molecularity. It might look similar for some reactions. Just serendipitously, it could be similar. Just by chance, it could be similar. But there is no like rule that says that okay, order is equal to molecularity. This is extremely different. This is a different concept. It looks similar, but they are different concepts. Also, it is very difficult to have 3 or more, like, okay, 2 molecules coming together colliding, okay. 3 molecules, okay, I mean, maybe 3 molecules could like be bombarding on each other with a particular orientation to produce. But 4, like when you move to 4 molecules colliding in a particular orientation, it kind of becomes more difficult. So the molecularity, like it's basically 2 or 3 generally, okay? So if you have a complicated reaction, can you imagine like if you have, say, 5 molecules on the reactant side, can you imagine that, okay, 5 molecules coming together in perfect orientation, in a perfect form, in a perfect energy that will collide and will give you a product? It's highly rare. And that is why you can see that for elementary reactions, the molecularity won't go maybe 4, but 5 kind of gets into really, really rare kinds of reactions will have a molecularity of 4 and higher. Okay, so there's the difference between order and molecularity. Now let's combine the concepts of equilibrium and rate, because these are very similar. And let's talk about a reaction which has been dealt with experimentally before. So hydrogen plus iodine gives 2Hi. So this is an experiment. So the rate of the forward reaction rate was experimentally determined to be some rate constant times the concentration of H2 times the concentration of I2. Now, it seems like we just took the stoichiometric coefficient, but no, I mean, it's not that simple. People did not know just by looking at this reaction that this was the forward reaction rate. They did experiments and they actually found out that this is the reaction rate. It's just by chance that these stoichiometric coefficients are 1 and 1, and the order is 1 and 1 each. So the overall order is 2 in here. Okay, in here, so the forward reaction rate is basically the rate of formation of, so rate of formation of Hi, right? Or the rate of like consumption hydrogen or iodine. Now, the reverse rate was also calculated. The reverse reaction rate was also calculated, and this came out to be, this was done experimentally, okay? This was just done experimentally and they found out this. So this is the rate of decomposition of Hi. Okay. Now, what is equilibrium, right? What is equilibrium? Equilibrium is that state of the reaction of that system in which the rate of forward reaction is equal to the rate of backward reaction, right? So at equilibrium, I write it in here. So at equilibrium, the rate of the forward reaction rate becomes equal to the reverse reaction rate, okay? So I can also write this as K forward and K reverse, just for easier recognition, okay? In here, what it becomes is Kf times H2 times I2 becomes equal to K times reverse times Hi squared, right? Now, if we try and find out the rate of so these are Kf and Kr are the rate constants for the forward reaction rate and the backward reaction rate. So these are constants. These do not depend on anything else. They are dependent on temperature. For at a fixed temperature, they are constants. So Kf by Kr becomes equal to Hi squared Hi times I2, right? Now this I call this fixed ratio, because Kf is a fixed number, it's a constant, Kr is a constant. So the ratio of two constants should also be a constant, and I call that constant K equilibrium. Okay. So this is the relationship between the chemical kinetics and chemical equilibrium, because this is just, chemical equilibrium is just a ratio of like the forward rate constant and the backward rate constant. This did not depend on any concentration with which it began. It did not. It was just a constant. It did not depend whether you started out with H2 or started out with Hi. So it did not depend on the direction of the equilibrium. So equilibrium does not depend upon the direction with which you come in, right? So if you can start with H2 and I2, or you can start with Hi, you'll get the same result. So it is sometimes represented in a way that looks like this. So if this is time, or the reaction, the extent of the reaction, and if this is say concentration of the species, individual species. So let's say you started off with the reactants. So the reactants have, say, some concentration, right? So the reactants have some concentrations, and after a while they flatten the curve and become something like this. And in here you do something like this. So this is the concentration. So this is basically the reactant side, right? So you have more concentration of the reactants when you started with time. The concentration decreases, and this red, so this is the reactant side, and this red gives you the reaction, the concentration of the product side. So you started off the products, and after a while this whole thing comes to an equilibrium, right? So at what state did this come at equilibrium? So you see that after this point, something like in here, you stopped making any changes, right? So from here, what we start is called equilibrium. So you do not change the ratio of the constant. So this becomes, this whole thing, this whole ratio, this becomes a constant. So this is the realm of equilibrium, and this whole realm is the realm of kinetics. Right? So you started off with unequal amounts of reactants, products, and they were not in equilibrium. It took some time, and we don't know what time it took. For faster reactions, this time can be in seconds, or slower reaction, this could be like millions of years. So it's or billions of years. So this whole thing can vary by like orders of magnitude. Okay, so it depends on what things do you call slow and fast. It's really relative. Okay, so when you start off, you have a kinetics realm, and then after a while, when the concentrations like reach an equilibrium, they don't change. These ratios don't change, and this is called the equilibrium region. Now, one more important thing to understand here is equilibrium doesn't mean that the reaction has stopped. This just means that at equilibrium, you are having a forward reaction, you're having a reverse reaction. So all these things are happening, but those rates are equal. So overall, the net, there is no net change in the concentration of the reactions. Okay, that's the meaning of equilibrium. It doesn't mean that there is no forward or no backward reaction. There is actually. So equilibrium is a very dynamic process. It's not static. So if the reactions, if the concentrations are not changing, that doesn't mean that it's static. It is a dynamic process. On the flip side, if you have a static if you have a static system, it doesn't mean it does not necessarily mean that the reaction is at equilibrium, right? So if you have a system and things are not changing, the concentration of neither of the things are not changing, that doesn't mean that these things are in equilibrium. This could just mean that they are not reacting. Maybe they need more time to react, right? So if you have a static system, that doesn't mean that the reaction is at equilibrium. It does not. If the concentrations are not changing, that is not a full proof evidence of a reaction at equilibrium. Okay, it might be slower. It might need just more time to do that. So it could just be that the curve is like really flat for a while, and then maybe after a while this might go down, go up, whatever. So this, since you have a flat line like this, doesn't mean that you have an equilibrium, right? Okay. So this is the relationship between order and between equilibrium and kinetics. And our last stop in here is to see how the rate constant, which is the K, the rate constant, changes with respect to temperature. So we saw that rate constant K is a constant, but it changes with temperature. We'll now see how it changes and how we can quantify the rate of change of K with how K changes with temperature.